Hello everyone and welcome to EAS4700. My name is Rupal Patel and I am Assisting Professor Dong for Aerospace Design 1 this semester. About myself, I finished my bachelor's in the field of Aerospace Engineering and Applied Mechanics from IEST, and I'm currently enrolled as a full-time grad student in the Department of ME. Over here, I am trying to pursue a specialization in both TSFD and SMDM, and I have a particular inclination for fluid structure interactions. I have previous work experience on projects pertaining to the shockwave boundary layer interactions, specifically missile structures. I am an international student from India, and as depicted from the images, I am very passionate about aerospace. So a very relevant question was asked during the office hours regarding a the phasing change required within the parking orbit for the rendezvous to happen. As mentioned in our problem statement, we have to transfer our DST to a 5 Sol parking orbit where our EEV is already located. However, to make the rendezvous between the two happen, it is highly probable that we need to transfer our DST to the location of EEV within the same orbit, and this is where our phasing maneuver comes in. In simple terms, phasing maneuver is a two-impulse Hoffman transfer done to a spacecraft which is required to be moved to a different location within the same orbit. The transfer orbit in a phasing maneuver is selected such that the spacecraft can be transferred to the new location within the orbit in a specified period of time. This feature of this maneuver is extremely useful for our case since we have a very tight mission deadline. The amount of change of the location required is measured in terms of phase angle, and this phase angle is further used to compute the amount of time required to make that location change happen using the Kepler's equations as shown over here. Once we know the amount of time required for the location change to happen, we can use that to find out the time period of our phasing orbit. And once we have the time period, we can compute the semi-major axis, apoapsis, and periapsis of our phasing orbit. Once we have all the variables of the orbit computed, we can simply follow the procedure of the Hoffman transfer and compute the impulse required to make this maneuver happen. So as shown over here, the delta V is the impulse required to change the spacecraft from the original, to change the trajectory of the spacecraft from the original to the phasing orbit. A very important thing to keep in mind while doing calculations for this maneuver is that it is a two impulse maneuver, and therefore the total impulse required would be twice of delta V. The first impulse would be provided to change the trajectory of our DST from the original orbit to the phasing orbit, and the second one would be provided to change its trajectory to back to the original orbit. So there can be two cases of a phasing maneuver, which depend on the amount of orbital time period change required. Imagine that our DST is ahead of our EEV. Then in that case, we have to increase the orbital time period of our DST so that it can catch up with the EEV, and in that case, we will follow a slower intermediate. The slower intermediate orbit over here is the slower phasing orbit. We will follow a larger orbit in order to make the rendezvous happen. And if our DST is behind our EEV, we will have to speed up our craft so that it can catch up with the EEV on time, and we would therefore use a smaller phasing orbit for the same. An important thing to notice in these two cases is that our rendezvous is happening at the same place where we provide the first impulse to our DST. This image is just to give an example with numbers about the cases which I discussed just back then. A more efficient form of phasing maneuver is when we do not it's an assumption that the rendezvous would happen at the same location as the location of the first impulse provision. A more efficient maneuver would be if the impulse is provided at a different location and the rendezvous happens at a different location within the same orbit. So this is the image for the same. It is completely similar to what I have explained earlier. This point is the place where our DST is provided the first impulse. If we have to reduce the time period of the same, which was our case 1 in the earlier slides, we will follow this faster orbit for the rendezvous to happen. And if we have to increase the time period of our chaser DST, then we will follow this larger but slower phasing orbit, and the rendezvous will happen at this position. Note that impulse 2 means that over here we are changing we are providing a deceleration so that the trajectory of the DST can be changed back to the original parking orbit. So this is phasing maneuver. This will be very useful for the docking of DST and EEV. Another application of this could be when we have to land our EEV on the Martian moons. In that case, the rendezvous would be with the surface instead of another spacecraft. It would involve a bit more calculations, but this is definitely a way in which you can compute it. If there are any doubts, please email either me or Professor Dong for the same, and we'll try to clarify them as soon as possible. Thank you so much, and see you in the next lecture.